Okay, so today, if you've looked through the notes already, you'll know that there's not actually really a lot to this. I'm basically going to talk through a couple of analogies to everyday life. There's some pictures of food, and then below that there's some analogies of tires and cars, and after that I'll show you some pictures of some molecules. And I'm going to do 3 examples. But today's topic is not actually anything new, it's just throwing a new twist in that we haven't really considered yet. So let me start with an everyday life example. Okay, let's say that you've got 6 loaves of bread, a big jar of mustard, and you got 3 pieces of salami. How many sandwiches can you make? I guess if you went with 1 piece of salami per sandwich, a little chintzy, but okay. I guess you could make maybe 3 sandwiches. The point I want to make here is that if we wanted to talk about reactants and products in chemistry, all of these would be your reactants, and your product would be a sandwich. That makes sense? You're going to have leftovers. You're going to have a lot of leftover bread and a lot of leftover mustard. Does that make sense? And sometimes in the chemistry world, we want to figure out what the leftovers is going to be because there's going to be something extra, right? If you have chemical A and chemical B react with each other, unless it is absolutely perfect that the amount of chemical A and the amount of chemical B are exactly matched up, something's got to be left over. Does that make sense? I mean, once in a blue moon it's going to happen, but there's always something excess. And so hence the topic limiting and excess. So I mean, the limiting one is going to be the thing that you run out of, and the excess one is the one that there's going to be leftovers of. So if I were to just kind of illustrate this, so this will be the one with leftovers. The leftovers would be the bread and the mustard. I mean, you'd probably have, maybe those would be the pieces of bread you'd use, because you'd use some of them, right? But there'd be lots of leftover bread. Mustard, I mean, if the container was full, it would be just slightly less full. Right? What was the thing that limited you? Clearly, the salami is going to run out first. Does this concept make sense? So, I mean, so long as you get the concept in an everyday life scenario, like I said, I love analogies. Now I just need to show you how to apply it to chemistry. But let me do my other analogies first here. Here I found a picture of, say there's 8 cars, and there's 48 tires. So in terms of a recipe, how does the recipe work? Well, for every 1 car, you would need 4 tires. That would make, 1 car with tires. Kind of a weird recipe, but does that make sense? So you have 8 car bodies, let's say. So this would be the first one, the second one, the third one, the fourth one, the 5th one, 6th one, 7th one, 8th one. Clearly there are going to be tires left over. Does that make sense? So our question once in a while is going to be not so much make a prediction as to how much you can make, but it's going to be make a prediction as to how much leftovers you're going to have. Does that make sense? So in terms of definitions or terminology, limiting reagent is the reactant. By the way, before I go on, do you guys know the term reagent? Have I ever mentioned this before? Okay, reagent is a broad term referring to either what's on the product or the reactant side. So if I were to give you a generic equation like A plus B equals C plus D. Okay. A reagent refers to anything of A, B, C, or D. Does that make sense? Whereas a reactant would be A or B, and a product would be C or D. Does that make sense? Reagent just refers to anything that's there. So it could be a product, it could be a reactant. Reagent is just anything. Okay. Whereas these are the reactants and these are the products. So limiting reagent is the reactant. It has to be on this side of the equation. Reactants have to be on this side, of which there's less of. And then the excess one is which there's more of. One more picture, and then we'll do some examples. So let's say that you have 10 hydrogen molecules and 7 oxygen molecules. And you want to combine them to make water. So first question, well, what is the recipe? Well, the recipe says that you need 2 hydrogens for every 1 oxygen. So, that could make a water. And that could make a water. And that could make a water. that could make a water. And maybe that one could make a water. So how many water molecules did I make? 1, 2, 3, 4, 5. Kind of makes sense, I guess. But again, does it make sense that clearly there are leftovers? These guys right here are leftovers. Or we would call them excess. So in this case, that would be the hydrogen that's in excess. So if you're doing a calculation then, should you do your calculations based on the excess or based on the limiting? Always do it based on the limiting. Because for example, let's say we started with, hang on, did I do that wrong? It's the oxygen that's left over, isn't it? Because this is, the little white ones are hydrogen, aren't they? I did that backwards. The oxygen, because this is hydrogen, that's oxygen, that's hydrogen, that's oxygen, that's hydrogen. So these guys that are left over are extra hydrogens, or extra oxygens. Ugh. Having a bad day. Does that make sense? Okay, so if I were to make some guesses here, if we had 10 H2s, according to this recipe, you get 1 water for every 2 hydrogens. So therefore, if you have 10 H2s, you should be able to make 5 waters. Makes sense? Or our recipe says for every 1 oxygen, you get 1 water. So if we have 7 oxygens, in theory, we could make 7 waters. Why didn't we make 7 waters? Well, because the hydrogen is what ran out. So the excess was this guy. This guy right here was the one that's limiting. So I guess the point I want to make here is that this work is not going to be harder. We're going to do exactly what we did before, only we're going to do double the work. We're going to solve a stoichiometric equation twice, and whichever one gives us a lower amount, that's the one that must occur. Kind of like the salami. Like in theory, based on salami, I can make 3 sandwiches, but based on bread, I can make 400 sandwiches. So which one am I actually going to make? 3 sandwiches. So you'd have to do double the work. So let's do some examples. No, I guess one more slide. You're going to be given the amount of both reactants, do the work twice. You should get 2 different answers. Pick the smaller one. Does that make sense so far? Yeah, let's do some examples. Like I said, it's not harder work. It's just, this sucks because it's more. But you're not doing more tricky work. You're just doing it twice as much. So here's our example. You've got some copper and some sulfur reacting according to the equation. Our goal is to figure out how much is actually going to be made. Maybe a follow-up question might be like, which one is going to be leftover? Are we going to have leftover copper, or are we going to have leftover sulfur? Well, you're looking at grams though, but we have to base it on moles. Does that make sense? Yeah. That's actually a good starting point though. Don't look at the grams number and say, hey, look, way more copper than sulfur, because it's not grams that really reacts at a molecular level, it's moles. So we just do the work twice. So first I'm going to do work for copper turning into Cu2S. So this is going to be step 1. And then later, step 2, so I'll leave some room, but later down here, we're going to do it based on sulfur turning into Cu2S. And whichever one of these 2 things gives us a lower number, that's what's actually happening. Like I said, with the salami example, based on salami you can make 3 sandwiches, based on bread you can make 400, but you don't have enough salami to make 400, so therefore we're only making 3. So, start with copper. We started with 10.6 grams of copper. What do we do next? Good. We don't want grams, we want moles. So hopefully by now it's getting faster. We need a grams per mole number.
Wouldn't you put grams?
Don't write it like I just did there. Yeah, because that's not going to work. Good catch. Copper is 63.55, I believe. So grams, moles. What comes next? We need a ratio. Yeah, now we need our recipe, basically, that says, well, how many moles of Cu2S do we get for every mole of copper? And the way this recipe works is that you need 2 coppers for every Cu2S. So 2 goes there. that recipe sometimes comes into play. Because let's say when you were making sandwiches, this might be a really weird sandwich, but let's say that it took 400 slices of bread to make a sandwich. That would affect things, wouldn't it? So like we would need to consider it. Like in terms of the sandwich, I guess the sandwich ratio is 2 slices of bread to 1 piece of salami, right? But in theory, if you made a really weird sandwich that used 800 slices of bread and 1 piece of salami, then maybe somehow salami you'd have left over. Really weird sandwich, obviously, right? But does that make sense? So you have to account for that ratio. And then last step, we need our molar mass, but now of our product. So I need some help here. Copper is 6355. Need 2 of them. And sulfur, I think, is 3207.
Yeah.
Okay.
159.17.
Thank you. Is it okay at this point in your chemistry career that we can kind of gloss over that step? You guys are okay with finding molar masses? Hopefully also you see why I really wanted to drill that into your heads at the beginning of the year. Because like, it's going to come up a lot. So, okay, so I got a calculator. I'll do this as well. See whether you guys get the same thing. 10.6 divided by 6355, also divided by 2, times by 159.17, means that you should expect 13.27460.268 grams. I'm going to hold on to all those numbers for now. I'll round later. So far, so good. Okay, so in theory, if we use all of our copper, this is how much we make. But maybe we actually end up using all of our sulfur. So now we do the exact same work, but we just tweak it for sulfur. So sulfur started with 383 grams. Molar mass of sulfur is 3207. It still is Cu2S on the top, but now on the bottom it's sulfur. And that was a nice 1-to-1 ratio. And then the good thing about doing these ones here is that a lot of the work is kind of similar, if that makes sense. Because like the ending half of your work, like you're still going to do the 159.17 grams per mole. Like this last step is kind of always the same. I'm going a little fast. Does this make sense though? Am I going too fast for you guys to follow? Okay, so let me just calculate it so that you get the same thing as me. 383 over 3207. It's a 1-to-1 ratio, so I'm skipping that, and then it's still 159.17. Based on this guy, I got 19.00, etc., and I'm going to not bother writing that number down anymore because this is clearly the bigger number. Okay, so this kind of sucks, but I'm going to put a big cross through this saying this is not what's going to happen. Why is this not going to happen? Don't write this out every single time, but this will not happen because copper will run out first. We do not have enough copper to make this much. So long as you can keep this right in your head, this now means that the limiting reactant is copper, and the excess reactant was sulfur. And that might be my question. Sometimes my multiple choice question would be, well, which one is limiting or excess? And so you just need to do the math. Whichever one comes in as a lower number, that's your answer. Does that make sense? Cool. Okay. I think I only just have this. No, I have 2 last examples here. Let's try another one, although why don't you guys do this one yourselves? Because I've kind of given you the steps, so that you can try it. I'm going to give you magnesium and HCl. This time I don't give you an equation, so that requires an extra step in there. Try to figure out how much of each product will be produced. So, I don't know, take a few minutes to see how far you get before I kind of jump back in again. So before you do anything, you need that equation, right? What kind of reaction's happening between magnesium and HCl? Good, yeah, single replacement. Yeah, you've got Mg solid plus HCl gas It's going to make Mg going with the chlorine. And hydrogen by itself. What is hydrogen? How does hydrogen go by itself, though?
H2.
Good, H2 gas. Good, okay. See if that can get you started. Throw a state of matter after MgCl, but I mean, is it really that relevant? Probably not. It's probably solid.
Oh, no. You know what? What is MgCl? Is there?
Could be aqueous, I guess.
It's just-
There's one more twist to this question. There's now 2 products. Don't do it 4 times, but you have to do it 3 times. So pick one of the products and go from like the first thing to that product, and then go from the second thing to that product and figure out which one of the 2 is limiting. Okay. And once you do that, then whichever one is the limiting one, then do it again going to the other product. So you don't actually have to do it 4 times, but unfortunately you do have to do it 3 times. So let me say that one more time. Go from A to C and go from B to C and figure out which one of A or B is the lower number. Make sense? Once you know who's lower between A or B, then go from, say, A to then D. There's no point in going from B to D because you already know that one's bigger anyways.
So does that mean you keep the HCl then?
It doesn't really matter which one you go from first, but like you're going to have to go from magnesium to something.
Uh-huh.
Let's say you go from magnesium to H2 gas. Then you're also going to have to go from HCl to H2 gas and figure out which one of those 2 is lower. And then once you figure out which one of those 2 is lower, let's say it's the H2, or let's say it's the magnesium. Then once you found out from magnesium to H2 gas, then you've also got to go back and go from magnesium to MgCl. Make sense?
Some.
Like I said, give it a try. I mean, I'll give you a head start here. I'll do it obviously still too.
So to recap,
Yeah.
A to D, B to D, and then A to C.
Yeah, whichever one is lower of A to B.
Oh,
Yeah,
okay.
exactly. That makes sense to me what you said. So if it makes sense to you, then.
Okay.
I hope you'd agree with me when I say that it's not harder work, it's just more. Which is really annoying, because it's like, oh, you gotta do the same thing 3 times.
So MgCl, we're just looking at the C. It's MG2.
You can see that one too.
So, yeah, and I'm just going to.
I'm gonna start up here just to kind of catch up. Don't look unless you need some hints.
Is 1 minus. Mg is 2 plus. Cl is 1 minus. Well, I'd like
I'm gonna go solid on that guy.
Mg is 2 plus, and Cl is 1 minus.
And you can see it. No, I mean, I can't see what the writing drawing,
Okay.
but anyway, I'm gonna.
Okay. So, Mg. So this first.
So I have a little bit of work on the board here. I don't know if you guys are this far. I went from magnesium to H2, and I went from HCl to H2 to start. Did anybody happen to choose that same orientation?
Yeah.
Okay. You also could have gone from magnesium to MgCl and from HCl to MgCl. So, but all I'm doing so far here is just figuring out which one of these two is the limiting one. So I just got to figure out which number is smaller. And then once I figure out which number is smaller, I cross off half my work and say, kind of sucks. Like, it feels really bad to me where it's like I do all that work and I'm like, and you're useless. So here's what I got. I got 0.839243109.8 grams. I'm going to do sig digs at the end. I want to hold on to all these numbers just because there's a good chance that I'm going to like have to do stuff with them later maybe. So. Alright, so I got two values. Did you guys get the same values as I did? Basically 0.8 of a gram if it's magnesium to hydrogen gas, and like way less if it's HCl to hydrogen gas. You guys get the same thing as me? Okay, so what does this imply? Which one of these ones actually occurs? The bottom one. So I mean, if it helps, at least at first, I like to maybe at first write out just what's happening here. So this means that HCl will run out first, and Mg will be leftovers. Like, I mean, you don't always have to write it up, but maybe just to keep track in your head. You can make a lot of stuff with magnesium, but you can only make a very little amount of stuff with HCl. So it must mean that the HCl is going to run out first, and you're going to have lots of magnesium left over. Okay. So now I'm going to do one more line worth of work. I need to go on line 3. Now I need to go from HCl to the other reactant, which is going to be MgCl2. That makes sense? So, based on that, I'm going to need to do almost the exact same work, only like little bits of it tweak. Like, it still start with 287 grams of HCl. I still need the moles over 3646. That hasn't changed. I even still need the 2 HCl on the bottom. But now it's like the ending that changes. I don't want to look for hydrogen anymore. I want to look for MgCl2. I need that molar mass though. 3545 times 2 plus 2431. I have a molar mass of 9521. Anybody gotten that far yet? Okay, good. So grams per mole. Okay, I'm going to be specific. This is of H2, and this one is going to be of MgCl2. 2.7 divided by 3646 divided by 2 times 9521. I got 3.747294 grams. Cool. Oh yeah, I mean, obviously do sig digs. I actually have a reason why I'm not doing sig digs yet. It's not for this particular question, but it's for a follow-up question we're going to do on our very last example as to why I'm holding on to sig digs so carefully. Devin. Which product do you do what for? Those first ones? I don't care. Like, if you figured out the magnesium chloride ones first and then crossed off the wrong magnesium chloride one, that's fine. Like, so long as your two answers were this answer and this answer here, you're good to go. Like, because you did have choices. Does that work? Okay, follow-up question then, which I want to do for this example here, though. Sometimes I might ask you how much extra magnesium will be left over. That make sense? Okay. Well, here is one of the ways you can solve it, and here's why I've been holding on to all of those decimal places. Okay. I'm just going to rewrite my equation here. It was what was it? It was Mg solid plus HCl gas made H2 gas. Yeah, that's ugly. Plus MgCl2. I'm just gonna call it a solid. I don't know. It doesn't really matter, does it? The reason why I maybe want to rewrite this, or I mean, I don't need to rewrite it if you have it somewhere nearby, is I'm gonna record underneath all of these reagents. It's a good word to use now. The masses that I've calculated. So the MgCl2 was 3.747294 grams. And the H2 would have been 0.075035656 grams. And then we knew the starting amounts, didn't we? So HCl would have been 2.87. And magnesium was 10.1. Okay, there is one way of solving this, which is the law of conservation of mass. I'm just going to add up on each side of the equation how much mass there was. So like on this side right here, you had 10.1 and you had 2.87. So to start with, you'd have had a total of 1297 grams. However, when you were done, 0.075035756 and 3.747, it was at 294. When we were done, we only had 3.8223 or so grams. We just broke the law of conservation of mass. Well, no, we didn't. Why didn't we? Because there's excess magnesium. Well, how do I find that excess magnesium? Good job, Brianna. You'd subtract those two numbers. Yeah. Because clearly we can't break the law of conservation of mass. That's supposed to be a law that, in theory, should happen, right? So one of the best ways of solving this is solve for all four things. Add the products, add the reactants. One should be way higher than the other. Why? Well, because of the extra, right? So subtract the two. And that's why sometimes I like to hold on to all these decimal places, because it can help, if that makes sense. So then I'll do my 1297 minus that number I just got. Now I'll do sig digs. So I've got an excess of 9.15. Magnesium is the one that there's extra of. That makes sense? Right. So again, I'm going to say this a lot today. It's not harder work, hopefully. It's just lots of it. There's a lot more. So hopefully by now, though, like you're getting kind of faster at doing all the stoic stuff where it's like, okay, grams, molar mass ratio, put the numbers in there. Hopefully you're getting pretty fast at like looking in your data booklet going, oh, what's the molar mass of this thing again? You find it kind of quickly. Because I think I've said this before. If you're one of those people who's like, oh, shoot, where is copper? You're looking one at a time. You just can't find where stupid copper is in your data booklet. Like, it's going to take you forever. You know what I mean? Okay, let me try one last example. This is the typical one then. I'm going to give you aluminum. I'm going to give you copper, sulfate. How much excess is there? So I just actually showed you how to solve this question then. Basically, you solve for all of the different things involved. Take products and reactants, subtract them, that's the extra. It's a lot of work. It will work, but I want to show you one more method. This one's a little bit faster because, I mean, clearly, like, there was, like, how much stuff was there on that last slide? Yeah. It's going to be a bit. So, if I ever ask you for the extra, there is one more way of doing it, but it does start the same as we just did before. So, first we need an equation, because we can't do anything without our recipe. So, you've got aluminum, which probably is solid, and you've got CuSO4, which, I don't know, I'm guessing it's probably solid. Again, does the state of matter matter? Not for us. So, I mean, just write something down. What's it going to make? Aluminum will then go with the sulfate, but that's not right, though, because aluminum is a +3, and the sulfate is a -2. Good, yeah, it'll have to look like that. I'll call it solid, sure. And the other thing will be copper. Probably solid. This one sucks. You need a 3 there for the sulfate, which means by default you need a 3 there for the copper, and a 2 for the aluminum. This one's a little trickier because we got, a different equation, but so far so good. Okay, the next step is exactly the same as we did before. We have to figure out which of these two guys is more than the other one is. So, actually, no, there's a better way of doing it. You know how sometimes we take like this number here and we turn it into those numbers over there? Maybe a faster way of doing it is, let's take this number right here and turn it into that guy there. Bear with me, just watch. Let's take 10.3 grams of aluminum, and rather than solve for how much products we react with, let's just solve for how much copper we would need. If that number is more than the amount of copper we have, then we have a problem. But if that number is less than the amount of copper we have, then we have our answer. Keep bearing with me. So, this is of aluminum. So what do we normally do when we do this math? Alright, so moles over grams, aluminum is 2698, I think. Okay. Rather than converting it to one of these guys over here, though, which we did in the last question, it took a lot of work. Okay. Let's just convert it to this guy here instead. So 3 CuSO4s and 2 aluminums. And last step, we need copper sulfate molar mass. So that's quite large, actually. Copper is 6355. Sulfur is 3207. Oxygen is 16, and you need 4 of them. Out of curiosity, do some of you guys have like numbers memorized yet? Like you have a few of them where you're like, I know that one already. It sure helps, doesn't it? At least the ones we always use, right? Like if you ask me what barium's molar mass was, I don't think I know it because we don't ever use barium. But like copper and iron and sulfur and oxygen, like I'm not saying you have to memorize them, but probably recognize it helps. Okay, I got 159.62. Anybody else?
Yeah.
Okay, good. Okay, here's what this means. After I do all of this work, this means that if I use up all of my aluminum, this is how much copper sulfate I would require. And once I find this number, I'm going to compare it to how much I actually have. So 10.3 divided by 2698 times 3 over 2 times 159.62. I got an answer of 91.4 grams of CuSO4. And I'm going to just write this word here. This is how much I would require to use all my aluminum. Do I have that much copper sulfate? What does that mean then? It means I'm not going to use up all of my aluminum. It means that I'm actually going to use up all of my copper sulfate instead. So you've got a 50-50 shot of this. If you take this guy and solve for this one, you might actually figure out your answer right away and know who's limiting. But we actually, unfortunately, picked the wrong one. So what I'm going to do now is I'm going to take my copper sulfate and solve for aluminum the other way. So here's how this would look. I've got my 50.1, yeah, that number, grams. And this is of the copper sulfate. And I'm going to do the that goes on the bottom, doesn't it? Moles over 159.62. And I'm going to go backwards and look for aluminum coming out of copper sulfate. And use aluminum's molar mass, which was this one here. So what I'm doing in this case here is I'm saying, well, what if we use all of the copper sulfate? How much aluminum would I require? And hopefully this number will be less than 10.3. Here's hoping. So 51.7 divided by 159.62 times 2 over 3 times 2698, and I got a value of 583. Anybody else get that?
Yeah.
So in context, I'm just going to write this out, and you don't have to write it out every time, but this means that this is how much grams of aluminum we would require to use all my copper sulfate. do we have at least this much aluminum? We do. So to find out how much extra there would be, see how this is maybe a little bit less work now? Take your 10.3 grams of aluminum, which is what I actually have, minus the 5.83 of aluminum I require. I'm being really thorough here. 10.3 minus 5.83 gives me 4.47 grams extra. That way might be a little bit easier because you don't have to do quite as much work. Also, you know how like I randomly chose to do aluminum to copper sulfate first? And then since that one didn't work, I had to go copper sulfate back to aluminum. You got a 50-50 shot. If you happen to guess the right one right away, you don't even have to do anything more than one line worth of work. It's kind of nice. Does that make sense? So, long story short today, so long as you get the concept of leftovers, which hopefully makes intuitive sense, right? There's a few different question types I could ask you. So one of the questions I could ask you is, well, how much leftovers will there be? Right? And if you do the method I just showed you there, you got a 50-50 shot at getting it in like one question. If not, you just do it twice. Makes sense? The other question I could ask you though is, how much products would you get? And that one usually takes more work because first you got to solve for like A for C, and then solve again for B for C, figure out which one is lower, and then once you figure out which one is lower, then you got to redo the other one and solve for D instead. Well, it takes a lot of work. Again, I said this a lot today, it's not harder work, it's just, there's just more of it. So hopefully you're getting good at this. All right, questions, comments, concerns, conundrums, curiosities, complaints, criticisms. Yeah, Tony, what's up?
I just had a question. Would it be smarter, would it be more intuitive to go with the bigger molecule?
To be honest, it kind of depends because you'd think that like, well, you have lots of copper sulfates. You'd think, hey, maybe this one is the one you'd have extra of. But that actually isn't how this one worked, right? Because this one had higher mass, but it had a lower, like it had a bigger molar mass too. But then the other thing is that like the ratio also matters. So I don't know that, I mean, you might be able to take an intuitive guess, but I mean, at the end of the day, I mean, if you pick the wrong one, then just do the other one. Yeah. So I don't know that I could always say like, hey, pick the one that's the bigger grams number to go with first, because it may not be. It's a good thing to try though. Other questions, concerns, complaints? Any other C words that I missed? You guys good? Okay, so for the rest of today and all of Friday, it's basically work time now. So I'm going to recommend that, work on your lab for sure, because that's due next week. But get a good start on your assignment now. I felt like a lot of you guys in the gases unit did a great job of always doing those assignment questions, like as you went through the unit, that you weren't like doing the assignment rushed right at the end of the unit. At least a lot of you I know were. And did that help?
Yep.
Like where it's like, if you're not doing the assignment after all of the tests, that's the right order, right? Because if you do it beforehand, then you're hopefully doing learning. Anyways, not me talking. Take a break. When you come back, do something. Whatever it is you do, I guess. Ask me questions if you need help.